Hello everyone. Today we're going to talk about comets, but this time it won't be about 13P Atlas. Instead, we'll explore the fascinating story of Comet 12P Pons-Brooks, an object from our own solar system that has been intriguing scientists with its absolutely unique behavior. This story perfectly illustrates why comets are among the most unpredictable and captivating objects in all of astronomy. There is a saying in the astronomical community that perfectly captures the nature of comets. They breathe the cats of astronomy, completely unpredictable. You never really know what to expect when a comet approaches the sun. Even comets that have visited the inner solar system multiple times can still surprise scientists with unexpected behavior. This unpredictability isn't a flaw in our scientific understanding, quite the opposite. It reflects the incredible diversity of these ancient cosmic objects. Each comet is unique in its composition, internal structure, thermal history, and rotational characteristics. When you combine all these factors with the complex physics of sublimation and interaction with solar radiation, you get a recipe for constant surprises. Before diving into the recent discoveries, we first need to understand what 12P Pons-Brooks is and where its peculiar designation comes from. The comet naming system might seem confusing at first, but it actually follows a set of logical rules established by the International Astronomical Union, IAU. The letter P indicates that it says a periodic comet, meaning one that regularly returns to the inner solar system, completing an orbit in less than 200 years. The number 12 shows that it was the 12th periodic comet ever catalogued by humanity. The names Pons and Brooks refer to the astronomers who discovered, or rediscovered, the comet during different appearances. Jean-Louis Pons was a prolific French comet hunter from the early 19th century, credited with discovering at least 37 comets, a record that stood unmatched for decades. William Robert Brooks, an American astronomer from the late 19th century, was similarly renowned for his comet discoveries. The fact that both names are attached to this comet reflects its complex history of identification across multiple returns. The original discovery dates back to 1812, when Pons first observed the object. Decades later, Brooks independently discovered what was initially believed to be a new comet, but meticulous orbital calculations later revealed that it was, in fact, the same periodic comet first seen by Pons. 12P Pons-Brooks is classified as a Halley-type comet, a category named after the most famous of all comets, Halley's Comet. This classification is not arbitrary. It refers to comets with orbital periods between 20 and 200 years, which typically originate from the scattered Oort cloud or the outer Kuiper belt. Pons-Brooks completes one orbit around the Sun approximately every 71 years. This means that once every 7 decades it returns to the inner solar system, approaches the Sun, develops its characteristic coma and tail, and then retreats back into the frozen depths of the outer solar system. Most people will only see this comet once in their lifetime, if at all. One of the most remarkable traits of Pons-Brooks is its tendency to undergo multiple outbursts during each return. Cometary outbursts are dramatic events in which sudden releases of gas and dust temporarily increase the comet's brightness, sometimes by several magnitudes. These eruptions can be triggered by a variety of mechanisms: the collapse of subsurface cavities, the sudden exposure of volatile material, or even impacts from meteoroids striking the nucleus. During 2023 and 2024, Comet 12P Pons-Brooks made its scheduled return to the inner solar system, a valuable opportunity for both professional and amateur astronomers around the world. With modern telescopes and highly sensitive detectors, the scientific community was ready to study this periodic visitor in unprecedented detail. Observers using medium-sized telescopes managed to photograph the comet, capturing stunning images of its diffuse coma and internal structures. But the most significant scientific work was carried out by major observatories equipped with specialized instruments. A team of Chinese researchers used the Tianma radio telescope to conduct systematic observations of the comet. Unlike traditional optical telescopes that capture visible light, a radio telescope detects radio waves emitted by specific molecules in space, allowing scientists to analyze the Comet A's chemical composition, activity levels, and even the physical conditions of the gases being released. Radio frequency observations revealed some remarkable findings. By working in two spectral bands, the L-band and K-band, researchers detected chemical signatures that defied expectations. In the L-band, they identified spectral lines of hydroxyl, OH. Hydroxyl is not a stable molecule naturally present in comets. Instead, it forms as a product of photodissociation, a process in which intense solar ultraviolet radiation breaks water molecules into simpler components. When an H2O molecule absorbs a sufficiently energetic UV photon, its chemical bonds can break, producing OH radicals and hydrogen atoms. Detecting OH allows scientists to indirectly calculate the comet's water production rate, a key measure of its activity. The calculations revealed something astonishing. At a distance of 1 astronomical unit from the Sun, roughly Earth AS orbital distance, 12P Pons-Brooks was releasing over 5 tons of water vapor per second. To put this in perspective, imagine 5 medium-sized cars being vaporized and ejected into space every second. This is an exceptionally high production rate, surpassing that of most known short-period comets. But the most astonishing discovery came from observations in the K-band. For the first time, ammonia molecules, NH3, were detected in a Halley-type comet. Ammonia is a volatile compound that sublimates at relatively low temperatures, and its presence reveals specific conditions during the comet's formation. This was a truly unprecedented finding. Despite decades of studying Halley-type comets with increasingly sophisticated instruments, ammonia had never been unequivocally detected in this class of objects before. 12P Pons-Brooks was revealing something fundamentally new about cometary composition. It's worth mentioning an interesting curiosity about 12P Pons-Brooks that captured public imagination during its appearance. The comet earned the nickname Devil's Comet due to a peculiar visual feature in certain photographs. In some images captured by amateur astronomers, the comet's coma structure displayed protrusions that vaguely resembled horns. With a bit of imagination, the overall appearance of the comet in certain orientations could look like a demonic face. The media quickly adopted this colorful nickname, and the Devil's Comet became part of the astronomical folklore of 2024. But behind this playful name lies a real physical phenomenon. The protrusions creating the horned appearance were likely collimated jets of gas and dust emanating from specific active regions on the rotating nucleus of the comet. As the nucleus spun, these jets traced patterns in space, producing the photogenic structures that so fascinated observers. Here we reach a crucial point that perfectly illustrates cometary diversity. Researchers compiled chemical composition data from multiple comets studied over the years, creating a comparative database. When they plotted the ammonia-to-water ratio on a graph, an interesting pattern emerged. Most comets formed a relatively cohesive cluster within the parameter space. There was certainly variability, but the majority of objects fell within a reasonably narrow range of NH3-H2O ratios. Even the famous Halley's Comet, the prototype of this class, fit comfortably within the main cluster. However, 12P Pons-Brooks was a striking exception. Its position on the graph was isolated, significantly removed from the primary cluster. If we judged purely by this chemical metric, one might even question whether Pons-Brooks truly belonged to the same category as the other comets. Here we reach a crucial point that perfectly illustrates cometary diversity. Researchers compiled chemical composition data from multiple comets studied over the years, creating a comparative database. When they plotted the ammonia-to-water ratio on a graph, an interesting pattern emerged. Most comets formed a relatively cohesive cluster within the parameter space. There was certainly variability, but the majority of objects fell within a reasonably narrow range of NH3 to H2O ratios. Even the famous Halley's Comet, the prototype of this class, fit comfortably within the main cluster. However, 12P Pons-Brooks was a striking exception. Its position on the graph was isolated, significantly removed from the primary cluster. If we judged purely by this chemical metric, one might even question whether Pons-Brooks truly belonged to the same category as the other comets. This understanding has direct implications for how we interpret other cometary objects, including interstellar visitors like 13P Atlas. When we observe a comet exhibiting unusual characteristics, whether it's an exceptional water output, atypical chemical composition, or peculiar orbital behavior, we cannot immediately conclude that it must be anything other than a comet. The story of 12P Pons-Brooks reminds us that comets are individuals. Each one carries a unique history encoded in its composition and structure, reflecting the specific conditions of the time and place where it formed billions of years ago. Why study comets that don't fit neatly into our established categories? Precisely because they expand our understanding. Every anomalous comet is a learning opportunity, forcing us to refine our models and broaden our knowledge. 12P Pons-Brooks, with its surprising abundance of ammonia, is telling us something about the conditions in the protoplanetary disk region where it formed. Perhaps this region was particularly cold, allowing ammonia to condense efficiently into ices. Or maybe specific chemical processes favored the formation of nitrogen-bearing compounds. Each possibility opens new questions and avenues of research. Fundamentally, comets are cosmic time capsules. They preserve primitive material virtually unchanged since the early days of the solar system. Most material in the inner solar system has been processed over time, melted, differentiated, or altered by geological and atmospheric processes. But comets, residing in the cold outer regions, remain largely pristine. When we study the chemical composition of a comet like 12P Pons-Brooks, we are literally examining a sample from 4.6 billion years ago. The molecules detected by radio telescopes condensed from the protoplanetary disk when our solar system was young. The isotopes present preserve signatures of nuclear processes from previous generations of stars. This understanding of cometary diversity is crucial when evaluating unusual objects. When the public, and even some scientists, question whether objects like 13P Atlas could be something extraordinary, perhaps artificial artifacts, the case of 12P Pons-Brooks provides valuable context. If a comet from our own solar system, observed across multiple apparitions over 2 centuries, can display characteristics so unusual that it stands apart from its peers in statistical analyses, then we should expect that interstellar comets, formed in potentially very different environments, may exhibit even more peculiar features. Modern astronomy teaches us humility. The more we learn about the universe, the more we realize just how diverse and complex it truly is. Categories that once seemed clear reveal themselves to be fluid upon closer examination. Objects we assumed were well understood can surprise us with unexpected behaviors. The 12P Pons-Brooks comet is a perfect example of this wonderful complexity. It is simultaneously a respected member of the Halley-type comet class and a deeply peculiar object that resists easy comparison. This apparent contradiction is not a problem. It is the essence of natural reality. So the next time you hear about a comet behaving strangely, remember, comets are the cats of astronomy. Unpredictable, fascinating, and always capable of surprising us. And that is exactly what makes them so valuable to science and so thrilling to study.